Hi, students. It seems like it's been a while. I'm not sure why. Last week we had our discussion about buffers and how buffers mainly maintain pH, and that's their job. Of course, I also looked at common ion effect, but I want you to think of everything as if whenever we have a mixture of a weak acid and its conjugate base, we more or less assume that this mixture has some buffering capability. I'm going to answer the questions that look at how such a weak acid, weak base mixture and its conjugate maintains pH. These are going to be questions number 41, 46, and 42. Okay, so we're going to get right into that. Question number 41. Consider a solution of a buffer A, which is 0.1 molar acetic acid and 0.1 molar acetate ion. Calculate the pH in each of the following cases. So now we already have a buffer, and it's 0.1 and 0.1 for the acid and its conjugate. What happens when we add 100 milliliters of A, which they called this buffer A, and 10 milliliters of HCl? So literally, we're adding to the buffer 10 milliliters of HCl. And there's also part B and part C, which we're going to look into. And here is part A. So again, we have acetic acid 0.1, acetate ion 0.1, and I'm just going to do this, you know, in the long way, is step by step. Of course, you could simplify these a lot easier when you get, you know, stronger at it. Calculate the number of moles of each of the acid and its conjugate. Of course, we have 100 milliliter of the buffer. Okay, so because we used 100 milliliters of A minus, so we have 100 milliliters of this buffer. All right, so to get the number of moles of the acid, we take the concentration multiplied by the volume. Now notice I kept the volume in milliliters, which means I'm going to get an answer which is in millimoles. To get it in moles, you have to multiply by 10 to the minus 3. I find it easier to put it in charts in the millimole form, especially if they give you milliliters in your volume. And the anion is as well 0.1, that's its concentration, times the volume. Now notice the volume is the same. Both the anion and the acid are in the same solution, in the same buffer of 100 milliliters. So you use the same volume. So the anion is also 10 millimole. How much acid are we adding? So we're adding 10 milliliters of a 0.1 molar acid. So if I take the concentration times the volume, again in milliliters, the number of moles of the acid which I'm adding is 1 millimole. Again, you all already know that HCl is a strong acid. In other words, it's simply H3O plus actively in solution with Cl minus as a spectator. Now what do? Okay, we have an acid, guys. We added it to the buffer. What happens? Come on, what happens? Click, clock, click, clock. Yes, the acid will react with the anion, with the A minus of my solution. So now we put a stoichiometric reaction between the acid added and the A minus, which happens to be the acetate. We put initial and final concentrations. Now, this is always a quantitative reaction, not always it can be complete. And even if it wasn't, just to let you know, no matter what the K for this reaction is, of course, this happens to be the K 1 over Ka, and in all cases, when I add acid to the anion, K, because look at the opposite side, it's simply the Ka of the dissociation of that acid. No matter what this K is, again, understand something. If I have a strong acid as a reactant, that's it. Let it go complete, okay? One-way reaction. I have 10 millimoles and 10 millimoles of my starting buffer. What did I add? I added 1 millimole of H3O plus. It's gonna react completely with my A minus. Of course, this becomes 0 in net because it's a complete reaction. You can always go back, call it epsilon, but overall, there's nothing left in solution of my H3O plus. It all has been neutralized into water. And the acetate picked up the H plus ion. What happened when this reacted? You'd say 10 minus 1, which is 9 millimole. And on the product side, this is 10 plus 1, which is 11 millimole. What do I have now in solution? I have an adjusted buffer. I still have the anion in solution. I still have the acid as a couple, and it's still a mixture of acid and its conjugate base, and therefore I have formed an adjusted buffer with new concentrations or new moles in solution. Now, of course, we can go ahead and calculate the concentration of the acid, take the millimoles divided by total volume. And now if you want to do this, keep the total volume in milliliters because it's millimole, divide by milliliters. And you can also get it for the base, and then you must apply Henderson. And we said we're allowed to apply Henderson all the time, and we're allowed to assume that the concentrations in solution of the acid and the base, at equilibrium is pretty much whatever I have left over in solution, because again, we're assuming that they are of weak strength and therefore the X is negligible for their reaction with water. Okay, nonetheless, I'm not going to repeat that. That's it. When I say Henderson from here on, we mean that we're just going to put the concentrations in solution. And of course, this is simply the pKa, which happens to be 4.76, plus log of the base divided by acid. Now notice, all I did was put the millimoles divided by millimoles. Why? Because the total volume is the same, and yet you could cancel it. So you really don't have to do an actual calculation for concentrations. Just keep the millimoles in there. You could also do it in moles. It's the same thing. Get a new pH, okay? So pKa plus log of this ratio. And notice the ratio does affect slightly the pH. The pH has decreased. It is now 4.67. Okay? And let's look at this change in pH. How did the pH differ? pH final in the final solution was 4.67. In the initial solution, remember, initially we had the same concentration of the anion and the acid. It was the same. It was both 10 millimole. And so the pH was simply equal to the pKa in my original buffer solution before adding the H3O plus. So the change in pH will happen to be minus 0.09. In other words, the pH decreased by 0.09. And frankly, that change is hardly much. So the pH decreased less than 0.1 of a value point, which is hardly any variation. Again, because we have a ratio here of the logs, you know, even if these concentrations change slightly, you know, the overall pH does not change much. It changes, watch out, but not much. Okay, part B of number 41. We have 0.1 mole, 0.1 molar of the acetate, and we're taking 100 milliliters of this buffer, and now we're adding 10 milliliters of OH minus. Now, when you add OH minus, let's see how much of that OH minus I'm adding. I'm adding 10 milliliters of a 0.1, and so if you multiply that concentration by the volume in milliliters, we get 1 millimole as in moles. So what should you do? Yes, exactly, a stoichiometric reaction. With whom? with the acid now, because the base, the strong base, will react with the acid of my buffer. Okay, so this strong base will be neutralized completely with the acid. So you do a reaction between the acid and the OH minus. Again, this now here, this is a complete reaction. Look, this is the K of this reaction happens to be Ka divided by Kw. If you go ahead and look at it, this is Ka, divide by Kw, you get the K of this reaction. Okay, so it is complete. Initially starting off, we had the same millimoles of buffer for the 2 anion acid. Again, that's the same question we had before. It's concentration times volume, where the volume is 100 mils of the buffer. But am I adding 1 millimole now of OH, which will be neutralized by my acid? My acid will give this OH an H, and so it becomes water. Okay, so now my acid amount will be decreasing in my solution due to neutralization, decreasing by how much? By the amount equal to the OH minus in my solution, and therefore this will be 10 minus 1, 9 millimole, and the amount of base now has increased, and this is going to be 10 plus 1 millimole, so that's 11. So we have what in solution now? We still have a buffer. It's my adjusted buffer with the new concentration of acid and base. So I simply use Henderson, and Henderson again is pKa plus log of the base divided by acid. Notice, all I have to do is the same millimoles I got in my chart divided by the millimoles left over of my acid, divided, of course, both by total volumes, but I don't need to include that because the volume is the same, so it cancels each other out, and it becomes a very simple calculation, which equals 4.85. What happened to my pH? It increased. Yes, of course, it increased slightly because I added OH minus, but not again by much. Look how much it increased. Though I added quite a bit, you know, but always my amount that I'm adding has to be limited relative to my acid, okay? Previous question, the amount should be limited relative to the base. The amount of pH change, well, again, final pH, which is 4.85, minus the initial pH, which happens to be equal to the pKa, 4.76, and therefore the pH rise by 0.09, and though this value is hardly changed, and so the pH is pretty much constant. Now, when we say pretty much constant, what I'm really comparing it with is with water, okay? I'm comparing it with water. So in part A and B, we saw how a buffer hardly changes its pH value when we added either a strong acid or a strong base. And here is an example where now we're going to add part C. We're going to add 10 milliliters of HCl only to 100 milliliters of water. So we're not adding it to the buffer, the HCl, we're adding it to pure water, okay? Let's see what happens when we do that. If I add HCl to water, of course, you all know that the HCl in my water will break up, will become H3O+. Let's look at this concentration of HCl. Okay, we have 0.1 mole and 10 milliliters, and we're going to divide it by the total volume of my solution, which happens to be 100 milliliters of water plus the 10 milliliters of HCl, which is 110 milliliters total volume. So the concentration of HCl in my solution is calculated, and it happens to be 9.1 times 10 to the minus 3. And you all know that that's it. This concentration is, of course, my HCl, which is greater than 3.2 times 10 to the minus 7, and therefore I can simply say the pH is minus log of that HCl, which is the H3O plus concentration. Take the minus log of this value, and you get it to be 2.04. Now let's see the change in pH relative to the pure water. Remember, pure water has a pH of 7. So how did, when I added this simple amount, this one, less than actually even 1 millimole, this is 0.9 millimoles. If I added that amount of HCl, what happens? The pH, the final pH is 2.04. The initial pH was 7 because it was pure water. The pH change is minus 4.96. Wow, that's a whole full number. That's minus 5 pH value points. And so when we mix in a buffer solution, a strong acid or a strong base, where they're limited in concentration, 10% by volume, not much, the pH practically does not change. However, when we mix a strong acid or a strong base in a solution of water, the pH varies greatly. And if you go back to the course, you saw that graph where we had a straight line for a modification of pH in a buffer when we're adding HCl, but the water, the concentration, the pH was greatly decreasing as concentration to water. Okay, so that was looking at how a buffer maintains pH. Question number 46. Okay, so we're looking at now question number 46, and I just did a correction of animation there. Okay, calculate the pH of a solution prepared by adding 0.25 mole of HClO4, which is called perchloric acid, HClO4, to 2 liters of solution composed of acetic acid, 0.5 molar, and acetate, sodium acetate, 0.4 molar. Now guys, from here on, anytime you see a sodium acetate or a salt like this, let's say you simply split it up in your head. Okay, we don't have to write it down. In your head, it's split up, and that means I simply have the acetate ion in solution, which is the conjugate base of this weak acid. Now, a lot of you, unfortunately, still have not memorized the strong acids, and I do highly recommend that you do. Because if you had, automatically, look, this is perchloric acid. In your mind, you're saying, okay, perchloric acid is a strong acid. That's it. So I'm simply adding H3O plus in my solution because the ClO4 minus is a spectator. And what happens when I add H3O plus to a solution, which happens to be a mixture of, it's a buffer, and it's a mixture of an acid and its conjugate base. What happens if I add H3O plus to that mixture, to that buffer? Yes, anytime you see that mixture, think buffer. Yes, that H3O plus will react with the A minus of my buffer, and it will react regardless in a one-way reaction, irrespective of this K, even if, you know, irrespective of it. Again, here I'm just going to put concentration times volume, a millimole chart, because we're going to do the stoichiometric neutralization reaction between the anion and the acid. So this is 0.8 mole. On the product side, concentration times the volume. And notice here, the volume happens to be in liters. And so we kept it in liters. So this happens to be a mole chart. So keep it in moles, okay? If your volume is in liters, keep everything in liters and in moles. How much H3O plus? It's exactly the amount of HClO4 minus, and therefore it is 0.025. We're going to neutralize it completely, of course, because it is the limiting reactant. And if it wasn't limiting anyways, this reaction would be a totally different thing, which again, we're going to see that. Okay, so this is limiting. It's going to be neutralized. 0 in the end, or epsilon if you want to call it. Here we have leftover anion, which is 0.8 minus the amount reacted 0.25 with the H3O plus. So I'm left with 0.05 mole. And here the acid, I am left with 1.25 mole at the end. So, well, they're not the same concentrations, and actually they're not very close in number of moles. And again, we're not really for first year going to look at what are these concentrations? Do they fit into the capacity of a buffer? Should we use Henderson? No, that's it, guys. I have an acid and its conjugate, use Henderson. Okay, what else? Pretend that X is negligible and this concentrations at equilibrium is simply equal to my concentrations in solution, and there you go. Now, if you change to second year chemistry, that you will learn beyond that. This now is 0.55 mole of the base divided by mole of the acid. Do I need volumes? No, I do not, because they cancel each other out. Calculate the pH from that Henderson. We have pKa is 4.74, and therefore my pH value is 4.38. Okay, 4.38. Well, let's see, did the pH vary much? Well, yeah, actually it did. It's some, it didn't vary a little. It varied, but not too much. I mean, not a full value point, okay? If you take the final minus the initial, this is minus 0.5 approximately, minus 0.4, okay? But still, not too much of a variance. Though this is quite a bit, this is 0.25 mole of acid. What is the pH of the solution? The pH is 4.39, and the closest value is A, so the answer is A. All right, now number 42 is again a three-part question, and we have a buffer, first of all, and this buffer is 0.2 mole of ammonia with 0.2 mole of the ammonium ion. So this is a weak base with its conjugate acid, okay? A base, weak base with its conjugate acid. Okay, to this buffer, we're going to add progressively 100 milliliters of this buffer, we called it S. We're going to add progressively some 0.1 molar HCl. The first time we're going to add 100, then we're going to add 200, and we're going to see, and then there's going to be part C of this question. So for part A, what is the pH of the buffer alone before adding anything? Of course, you all know we should use Henderson, that's it. And the acid, the base ammonia and its conjugate acid ammonium happen to be of the same concentration. And the pH, therefore, if these are the same concentration, is simply equal to the pKa, and you are done. That's it. The pH of this buffer initially is equal to the pKa, and that's actually the best type of buffer when the concentration of the acid and the base are the same and quite high. Part B, we're gonna now start adding some acid, okay? So part B, number 1, we're gonna add 100 milliliters of HCl. When we add 100 milliliters of HCl, automatically get the number of moles of HCl added, and that's concentration times volume, which is 10 millimoles, where I use the volume in milliliters. Of course, do a stoichiometric chart again with the reaction going one way, again, irrespective of the K value, okay? As long as I have acid as a reactant, just go one way, reaction complete. Initially, we have 20 millimoles of the ammonia and 20 millimoles of the ammonium ion, because I took the number of moles multiplied by 100 milliliters of the buffer. And I had 10 millimoles added of my HCl. So of course my HCl is limiting in this case, so this amount is less than the amount of my base. Therefore, it's gonna tend to 0 at the concentration, my base left over will be 20 minus 10, which is 10. And my added on the product side is my ammonium. The ammonium new concentration now will be 30 because it's 20 plus 10, which is 30 millimole. What do I do now? Automatically, I have acid and its base. You use Henderson. Irrespective of anything else, you just take the millimoles of the base divided by the millimoles of the acid. Ignore the T volumes because they cancel each other out, and equals the pH of the new solution or of the new buffer is 8.72. Well, again, a slight change in the pH. You know, it went from 9.2 to 8.7, some 0.4 values or 0.5 values difference in the pH. Now, what happens if I add 200 milliliters of HCl? Well, do the calculation of the number of moles of HCl when that is 200, and you get concentration times the volume, 20 millimoles of HCl added. And so you know HCl again is strong, so that's simply H3O plus. And who will it react with? Yes, it will react with my base of my buffer. Who's the base? It's the ammonia, not the ammonium. So neutralizing reaction of the H3O plus with the base of the buffer. Again, this now we have 20 millimoles and 20 millimoles as reactants and products. Now, who's the limiting reagent? Whoops, H3O plus is no longer limiting. Wow, it's the exact same amount as my ammonia. So both of them, this we call equivalence, and we're gonna see this when we get to titrations. There's equal number of moles of each, and therefore both will tend to 0. Both of them are equal. So if I say minus 20 here, both are gonna be 0, 0. Plus 20 millimoles on the product side, we get 40 millimoles of ammonium. So what is my new solution? Look at the new solution. Do I have any ammonia left? No, I only have ammonium ion in my solution. Do I have any H3O plus left? No. My solution is simply a weak acid. What's of ammonia? We'll calculate its concentration, take the millimoles, divided by the total volume. Of course, the total volume is again 200 milliliters plus 100 of my buffer, so it's 300 mils. Now I converted this into moles and milliliters, so you don't, liters, so you get an exact concentration. You could also keep it millimoles divided by milliliters, you get the same concentration. Now, yes, I have to get a concentration for the ammonium, in my solution, because now we're doing a weak acid pH calculation. Do you still remember how to do a weak acid pH calculation? Of course you do. You check if the concentration is greater than 100 Ka. Look at the Ka is 10 to the minus 9.2. So of course this concentration is greater than it. Then you choose the equation, the proper equation, which it will be now, it's this pH equals half pKa minus half log C. And you substitute in the pKa value, substitute in the concentration. I'm hoping that you get these concentrations correctly, and you get a pH. Of course, you can check this and see that this pH is less than pKa minus 1, such that it allows you that this is the correct equation as well to use. This is indeed a pH value less than pKa minus 1. pH happens to be 5.04. Try this on your own, get a piece of paper and pen and try it. If you don't do that, trust me, just watching the videos is useless. Okay, so again, that fits, of course, the simplified equation for a buffer, for a weak acid, sorry. Now a buffer, the same buffer, 0.1 ammonia with 0.2 ammonia with 0.2 ammonium. And now we're going to okay, and now part C of the same question. We still have the ammonia and ammonium. And part C says, to the solution obtained in part 2, which was, remember, part 2 was when we added HCl at 200 milliliters and again, that's when we only had left over ammonium in my solution. And we said we added to that 3.2 grams of sodium acetate. Again, the acetate simply remove the sodium. That means that I'm adding acetate ion. And they gave you the molar mass without changing the volume. So we had no change in volume, and the total volume obtained in part B was 300 mils. Calculate the pH of the new solution obtained. Okay. So what are we adding? Sodium acetate, okay? And we're gonna calculate the number of moles. They gave us grams, so grams divided by molar mass gives you the number of moles of the sodium acetate added, and of course, the number of moles of sodium acetate is the number of moles of the acetate added. Okay, so from part B, we had 0.054 moles of ammonia, and if we add to that same solution 0.4 moles of the acetate, what does that give you? Ammonium, 0.4, acetate, 0.04, sorry. Both of the same concentration. What is this? This is as if I have a salt of ammonium acetate because they have the same concentration. So it's like a salt of ammonium acetate. And this is actually a simple mixture of a weak acid and a weak base, but of two different couples of equal concentration. And remember, when we have this type of a mixture, or when we have a salt of the same concentration, what do we have? We use pH equals half pKa plus pKa2. So for each pKa's of each of the couples, half pKa of the ammonium is 9.2, pKa of the acetic acid is 4.76, and therefore the answer is 6.98. Okay, so it's as if I simply have a salt of ammonium acetate or a weak acid, weak base of the same concentrations in solution. I use the same equation. Okay,